Today we're going to look at related rates. So related rates is when we examine two or more rates with respect to a change in time. All right. So this is for us, it's going to be with respect to a change in time, but generally this process could be applied to other situations. So as I was saying, if we were talking about the area of a circle, for instance, we'd be taking our derivative. So we'd look at the derivative area with respect to time. Just like we learned yesterday with implicit differentiation, whenever we have the derivative of a variable, we're going to include the rate with respect to that variable. So yesterday we were looking at dy dx. Today we're going to look at dA dt and dr dt. So the derivative of r squared would be 2 pi r, and we include that rate dr dt. So now we've got two rates that are related to each other, right? The change in area and the change in radius. So if our change in radius gets faster, then we would expect our change in area to get faster. So this equation, which we have found by doing the derivative of our area equation, relates the rate of change in the radius, so if our radius is expanding, to the rate of change in the area. So that's what related rates are all about. Take a moment and write the steps down that we've got here. We're always going to start by drawing ourselves a diagram and identifying our values and variables. Then we're going to specify what we're looking for with the given information, and we're going to figure out an equation that relates the variables we have and the rates of change we're interested in. We're going to differentiate that equation, and then we're going to substitute and solve for the quantity that we're looking for. So I've got a few examples we're going to look at as our I do's today, and then I've got quite a few that will be our practice, and then a few for you guys to try out. So let's consider a spherical ice ball melting at a rate of 3 inches per hour. So spherical, we're going to start by drawing our diagram. I've got a sphere, I've got some radius, right? And the volume equation I've written here, 4/3 pi r cubed. You are going to need to know some basic volume and area equations for these problems, but I went ahead for this practice and the problems you're going to turn in and put in most of the equations you're going to need. So let's go through the problem and identify what we know. We know the ball is melting at a rate of 3 cubic inches per hour. That cubic inches is tipping us off that it's the change in volume, right? So since we're talking about a change, like that per hour, that means we're looking at a rate. It's melting, so it's going to be -3, and we're always going to include our units because that's going to help us when we get to the interpretation part at the end. When the diameter of the ball is 14 inches, at what rate is the radius changing? So we're looking for the dr dt, the rate of change of our radius, and we're told that our diameter is 14 inches at the time we're looking for the rate of change in the radius. So first we have to kind of look at our equation and say, well, our equation has volume and radius in it, and our information that we're given talks about the change in volume and the diameter. So we need to get from diameter to radius. We know that diameter is the whole way across the circle, and the radius is halfway across the circle. So radius is half of our diameter, which means we have to multiply the 14 times 2. Times a half. Yikes. And when you do that, you're going to get 7 inches as your radius. So now we have our known quantities. We have our variable equation, which relates the radius r to our volume. So we're ready to differentiate. So if I differentiate, do the derivative of volume with respect to time, I bring down my exponent with that r, make the exponent one smaller, and then I include the rate for the change in radius. 3 times 4/3, those cancel, so I've got dv dt, the rate and change of my volume, equals 4 pi r squared dr dt. I'm going to substitute in my known values, but first let's review what we're looking for. So this guy is telling me the rate of change in my volume. And this guy is telling me my rate of change of the radius. So if we're talking about what we know, well, we know dv dt, we know this guy, and we know the radius, this guy. We're trying to solve for dr dt, the rate of change in the radius. So we'll be substituting in. So when we do that, we've got -3, write a little higher, equals 4 times pi times r squared, 7 squared, times our unknown dr dt. So I've got -3 equals 4 times 7 squared times 49, which is 196 pi dr dt. So if we divide both sides by that 196 pi, we'll have our rate of change in the radius. So we've got dr dt equals -3 divided by 196 pi. Our unit for radius is inches. Our unit for time is hours. So we'd say the radius of the ice ball is decreasing at a rate of 3/196 pi inches per hour. That interpretation is important for our problem, so that's going to be the end of our solution. Let's go ahead and look at the next one. This one's a little different because we're talking about a cone. So conical paper cup is 3 inches across the top and 4 inches deep. It's full of water, so this cup's brimming with water. It springs a leak at the bottom and loses water at a rate of 2 cubic inches per minute. So remember, cubic signals to us we're talking about volume. So we've got dv dt. It's a leak, so -2. We haven't established what those first two quantities are, but we'll do that in just a minute once we look at our equation and we have our diagram. So how fast is the water level dropping at the instant the water is 3 inches deep? So that's also going to be important. Express your answer in inches per minute. So let's draw our diagram. So this is what a cone looks like, right? Where our height is this vertical and our radius is this piece here. All right. So let's identify what's known at the beginning. So we know that the whole way across the top of the cup, so from here to here, is 3 inches. We're told that. And then we're told that the height to start is 4. So we've got an initial radius is half of 3, so 1.5 inches. Initial height is 4 inches. Then we're asked, how fast is the depth of the water, or height, changing? That's what we've got here. The water level dropping when the height is 3 inches. So the quantities we want to relate are dv dt, our change in volume, and dh dt, our change in height. We have a height that's given, all right? But you'll notice our equation over here is a pesky r. We don't want that r squared in there. We don't like that guy. He's got to get out of town. So to get him out of town, we have to relate our r to our h. So to do that, we have to say, well, what ratio do we have for r over h? So that ratio is going to stay constant throughout the problem. So we've got r over h. If we're thinking about initially, we've got 1.5 over 4, right? So that tells us that 4r is equal to 1.5h. We want to get rid of the r in the equation, so we're going to divide both sides by 4. And then we've got r equals 0.375h. So we're going to substitute that into our equation before we differentiate. So our equation, v equals 1/3 pi times 0.375 squared h. Oh, I'm missing an h here. So when we do 0.375 squared, divided by 3, you're going to get 0.0469 pi, and then h squared times h is h cubed equals v. So now we've got just the two variables we want, v, the volume and the height. So we're going to differentiate. I recognize this problem is significantly harder than the last one because we had to relate the radius to the height, but we're going to do more of this, so I don't want you to feel like this is like you're out of your depth, okay? And once we have this equation, we just substitute in what we know. So we know we've got -2 for our change in volume. 1 times 3 squared dh dt. And then we rat-a-tap-tap on our calculator. If I can get that operational for us, we've got 3 squared, which is 9, times 0.141, which is 1.269. Pi dh dt equals -2. Divide both sides by that 1.269, and you're going to get dh dt equals -2 over 1.269 pi. Our units for height are inches, inches per, and then the time was measured in minutes. So for this, it would be the water level is decreasing at a rate of -2 divided by 1.269 pi inches per minute.